This video is going to provide a short introduction to the interactions involved in forming metal-metal bonds, or compounds where there's a formal bonding interaction between two or more metal centers. We're going to primarily be concerning ourselves with some metal zero carbonyl compounds. And we can look at some general bonding trends that are observed in these particular compounds. In general, group 6 metal carbonyls, or the chromium group, form hexacarbonyl compounds when the metal is in the zero oxidation state. So, compounds that are in nominal OH symmetry. If we go up to group 10 compounds, these primarily form 4-coordinate species with the metal site in nominal tetrahedral symmetry. Between group 7, group 8, and group 9, you no longer form mononuclear metal compounds. For the group 7, where the metal zero is in a D7 electron count, you form dimeric cobalt decacarbonyl species, where you have a formal metal-metal bond, and your CO ligands are staggered relative to one another. In group 8, you form a trimeric species with 12 carbonyls, so it's a dodecacarbonyl species. You form a triangle of metals, and then each metal center has 4 CO ligands associated with it. With the group 9, or the D9 species, you form tetramers with 12 carbonyls. The metals form a pseudo-tetrahedron with each metal center containing 4 carbonyls, or 3 carbonyls. With your group 7, 8, and 9 carbonyl compounds, you have a formal metal-metal bond between one or more metal centers. In this video, we're going to discuss the manganese decacarbonyl species, which is representative of group 7 metal carbonyl compounds that contains this metal-metal single bond. And we're going to explore the driving force for formation of that metal-metal bond. But first, we're going to go through and look at some general trends in metal-metal bonding. So first, D1 and D2 species typically do not participate in metal-metal bonding. The exception is if you have a bridging ligand that would support two metal centers being close together. So you can form these in some cases where you have bridging ligands. D7 and D8 compounds form metal-metal single bonds. D3 and D4 species can form metal-metal multiple bonds with the D3 species supporting metal-metal triple bonds and the D4 species supporting metal-metal quadruple bonds. These polynuclear type clusters here can be formed using a variety of different DN counts. So now what we're going to do is we're going to look at the orbital interactions on the metals that leads to different types of bonding interactions between two metal sites. We're now going to just look at bringing two metal centers close together to form a bond along this axis. And we define our molecular axis system with the z-axes pointed like that. We can define the y-axes going this way. There's the x-axis there, and the x-axis there for that other metal center. And we're going to look at the interaction between several different types of metal-based atomic orbitals. The first we're going to look at is what happens when we bring a dz squared plus a dz squared, when we bring those together. So we're going to have dz squared and a dz squared. We can form our antibonding and our bonding interaction. So the resulting bonding interaction gives you something that looks like that, while the antibonding interaction looks like that. If we look down the metal-metal bond, what you find is that this has cylindrical symmetry about that metal-metal bond. This is therefore a metal-metal sigma bond. This, its antibonding counterpart, is your metal-metal sigma star orbital. We can now look at a dxy plus a dxy. So here, the dxy, another dxy, forming a bonding and an anti-bonding combination. The bonding combination looks like this. The anti-bonding combination looks like this. We would refer to the bonding combination as a metal-metal pi bond, and the anti-bonding combination as the metal-metal pi star. Finally, we can look at a dx squared minus y squared plus a dx squared minus y squared coming in together. So, drawing these out, where we now have the faces of the d orbitals coming in contact with one another. So these lobes can all overlap. get a bonding and an anti-bonding combination. Your bonding combination, I'm going to try to draw this. Looks something like this. Your anti-bonding combination looks like this. We've now formed a delta bond. So this is a metal-metal delta bond, and the anti-bonding combination is your delta star. In terms of strength of these bonds, the sigma bonding interaction is the most favorable, so it'll generate the strongest type of bonding interaction, followed by the pi bond, followed by the delta bond. We're now going to look at the dimanganese decacarbonyl compound. If you take solid manganese and you put 200 atmospheres of CO over top of that, you do not form the manganese hexacarbonyl species. Instead, you form the dimanganese dodecacarbonyl dimer. Furthermore, the coordination geometry about the manganese centers is a staggered D4H. Okay, so it's not eclipsed, it's staggered. We can explain the instability of the manganese hexacarbonyl species, the stability of the manganese-manganese dimeric compound, and also the staggered coordination geometry using simple ligand field arguments. We're going to start by considering the hexacarbonyl species. And the d orbital splittings, you have your Eg star orbitals and low energy T2G orbitals. Manganese 0 is a D7 metal center. So we have 1, 2, 3, 4, 5, 6, 7 electrons. Carbonyl ligands are strong field, so it's going to be low spin. And what we have here is an electron in an antibonding orbital, meaning that the group 7 carbonyl compounds are going to be less stable than the group 6 hexacarbonyl compounds. So let's see what happens when we go from this 6 coordinate species to 5 coordinate in nominal C4V symmetry upon loss of that CO ligand. So to a first approximation, the dx squared minus y squared is going to remain unchanged. Also, the dxy is going to remain unchanged. Upon loss of this CO ligand, the dz squared is going to come down in energy. Remember, this is an antibonding orbital, and this is an antibonding orbital. However, we've lost the ligand, so it's now less antibonding than it otherwise would have been. So it's going to become slightly more stabilized in energy. In carbonyl compounds, which have pi acceptor ligands, these T2G orbitals are bonding orbitals. So the loss of that axial CO is going to cause an increase in the energy of the dxz and the dyz. So these are now less bonding in nature. Going through, putting in electrons, we have this. And what we have is this dz squared orbital that has an unpaired spin in it. And this is aligned along the molecular z-axis. So if you think about it, we can bring these two dz squared orbitals together to form an electron pair bond out of those. We're now going to go through and do just that, where we're going to have our two manganese pentacarbonyl species coming together to form the manganese-manganese dimer in the center, and we're going to stagger these. So we have our dx squared minus y squared, followed by the dz squared, dxz and dyz, and then finally the dxy. So bringing these two d orbitals together, you're going to form your metal-metal sigma bond and a metal-metal sigma star. Now, because these are staggered relative to one another, the overlap in the pi type fashion and the delta type fashion is going to be incredibly weak because the orbitals aren't directly lined up relative to one another. So going through and doing these interactions, you have this for your delta star, your pi star, and then delta and delta star here. Putting in the 4 electrons, 7 from each manganese center for your 14 electrons. We have this, where we have electrons occupying the sigma bond and an empty sigma star. So the sigma bond corresponds to the HOMO, and this corresponds to your LUMO. So first off, we can calculate a bond order for the metal-metal bond, and that's just 1/2 the number of bonding minus anti-bonding electrons. So we have 1, 2, 3, 4, 5, 6, 7, 8 bonding electrons minus 1, 2, 3, 4, 5, 6 anti-bonding electrons, which equals 1. So we have a metal-metal single bond as signified in this structure right here, because the delta orbital has a corresponding filled delta star and the pi's have a correspondingly filled pi star. Because there are no net bonding interactions in a delta or a pi type fashion, there's no driving force for these to have maximal overlap. Because of this, this is going to allow for rotation of these bonds, because the only net strong bonding interaction is this manganese-manganese single bond, which is cylindrical in nature. There's no pi or delta type overlap. So the geometry of this can be driven by sterics because there's nothing to gain by having strong overlap with these orbitals. In fact, strong overlap with those orbitals will actually lead to a slightly destabilized structure. Furthermore, we can also see where the driving force is for this manganese-manganese bond formation. So I'm just going to put electrons into our fragment orbitals. I'm going to put this as an up spin and this is a down spin. And here we have these DZ squares are formally anti-bonding type orbitals, as is the dx squared minus y squared. What we're doing is we're taking electrons from high energy anti-bonding orbitals and we're making them bonding in nature. So this energy stabilization is your driving force for formation of that metal-metal bond. And we can probe the exact energy of stabilization by looking at this excitation going from the metal-metal sigma to the metal-metal sigma star orbital using UV vis spectroscopy. And the energy of this transition will give us an indication of how stabilized this metal-metal sigma orbital is, and in turn an indication of the metal-metal bond strength. So we can look at some complexes, measure the energy of the sigma to sigma star transition. We're going to do this in wave numbers. And we can also determine bond dissociation energies of that metal-metal bond. I'm going to start by just looking at the dimanganese complex. And this has an energy of approximately 29,750 wave numbers. And the corresponding metal-metal bond dissociation energy in kilocalories per mole is 37 kcal per mole. You can form these compounds with all group 7 metals. So you can make the technetium species. What you find is that the energy of that sigma to sigma star transition increases. So it goes to 32,400 wave numbers. And the bond dissociation energy is approximately 45 kcals per mole. And then finally, the direnium complex. This has an even more energetic sigma to sigma star transition at 32,800 wave numbers and a bond dissociation energy of 53 kcals per mole. So what we're seeing is a systematic increase in the energies of that sigma to sigma star and a corresponding increase in the bond dissociation energies, showing that that sigma orbital is becoming more stabilized as we go down the group. The reason for this has to do with effective overlap of the DZ squared orbital. So if we look at radial distribution functions, so here's distance in some distance unit and the probability of finding it at some point squared. And for 3D, this would look like this. Going to a 4D, the orbital extends out further. And then finally, for the 5D, it extends out even further. What this is allowing for is increased overlap of the dz squared orbitals as you go from the 3D to the 4D, to the 5D. So here you have a significant amount of orbital overlap, and that systematically decreases as you go from the 3D to the 4D to the 5D. As overlap increases, the interaction between those orbitals are going to increase, and that corresponding sigma orbital is going to become more and more stabilized energetically. This is a common feature. If we look at metal-metal bond dissociation energies, first row transition metals are much weaker than second row transition metals, which are generally weaker than third row transition metal-metal bonds. We're now going to very briefly talk about the origin of metal-metal multiple bonds. So for high DN count metals, we form metal-metal single bonds, and these are signified by metal-metal distances on the order of about 3 angstroms. If we go to a D4 metal compound, these form metal-metal quadruple bonds. And these have short metal-metal distances that are on the order of about 2 angstroms, give or take 0.2 of an angstrom. Both of these have a metal-metal sigma bond formed from dz squared overlap. Where these two differ is in their ability to form strong sigma and delta bonding interactions. So as we already said, for the dz squared, you have a staggered type orientation. Because of this, there's minimal overlap between the dxy and the dxz and dyz type orbitals. So the corresponding sigma and or delta and delta star and pi stars are not that different in energy than the starting atomic orbitals. When you start forming metal-metal multiple bonds, you start to enforce eclipse geometries. So the ligands on the two metal centers are eclipsed relative to one another as opposed to staggered when you have the metal-metal single bond. Because of this, your corresponding bonding and anti-bonding interactions indicate very strong bonding. So with the XY, you form a low energy delta and a high energy delta star. With the pi and the pi star, you form a low energy pi and a high energy pi star. For illustrative purposes, I'm going to put in where the corresponding sigma orbital is. So here's your metal-metal sigma formed from the dz squared overlap. Here, because of that short metal-metal bond, this dz squared interaction drops very low in energy. And then the antibonding orbital goes up higher in energy. So there's your sigma type bond. As we already stated, with the 14 d electrons available, you have this, and the corresponding bond order equals 1. Over here with the d4, you have 8 d electrons. 1, 2, 3, 4, 5, 6, 7, 8. So if we're looking at the bond order for this, what you get is a bond order equaling 1/2 of 8 minus 0. So your bond order equals 4. It's a quadruple bond. It contains 1 sigma bond, 2 dd pi bonds, and 1 metal-metal dd delta type bond. So this is the origin of that quadruple bond in d4 metal-metal dimers.